Okay, for the other three functions, y equals cotangent x, which is defined as cosine x over sine x. I'm going to do the shortened version of that because it's going to look very much similar to the tangent function, but I want you to see how we develop the graph for this. We're going to develop it the same way as we did for the tangent. Okay, we're going to find the zeros of the sine function, and those are going to be our asymptotes. Well, we know that sine is 0 at 0, pi, 2 pi, and so on. So 1, 2, 3, 4 tick marks, 2 pi, pi, negative pi, negative 2 pi. I'm going to make my asymptotes at the y-axis. I'm going to make it at pi, at 2 pi, negative pi, negative 2 pi. So again, the zeros of the bottom give me the asymptotes for cotangent in this case. Also, the zeros of the top, where cosine is equal to 0, is pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So very much similar to the way we developed the tangent picture at this point, right? Okay. So let's see what happens if we go between 0 and pi for the cotangent function. Okay. So with the cotangent function, okay, in the first quadrant, cotangent is positive, right? So that means it can't have the same kind of shape as the tangent because that would be in the negative part between 0 and pi over 2. We don't want that. Okay. And as it turns out, if we start plugging in values like pi over 6, pi over 3, pi over 4, and so on, and plot some points, turns out that the cotangent graph, okay, ultimately kind of looks like the rotation of the tangent graph, 180 degrees essentially. Okay. So each of the areas, if we plot enough points, okay, and really all we really need here is 3 points. We can do the ones again, and I kind of missed the one over here. I should have made that a little wider. Sorry. Okay. If we plot the ones, okay, on each of these regions, then we can get a graph of the cotangent function. And when we get all done, okay, very much like the tangent function, except for it's like it's flipped essentially over the x-axis, and also the asymptotes are different. Okay, as soon as we draw those asymptotes, okay, that's going to define where the function belongs. Okay. Questions on the cotangent? Okay, secant, remember, is defined as 1 over cosine. So when we do secant, its asymptotes are going to be where the cosine is equal to 0, and the cosine is equal to 0, okay, at pi over 2, 3 pi over 2, and so on. So when we graph this, the asymptotes are going to be exactly what we had for the tangent function. So I'm going to go ahead and draw in my asymptotes. Negative pi over 2, pi over 2, 3 pi over 2. Okay. All right, and keep in mind that the values of the secant are just the reciprocals of the cosine. Okay. Now, what I want you to do on this here, and I'm going to put it in a different color, and it may or may not show up that well because the green looks pretty dark here and I don't have any other colors, but I'm going to, on this graph, I'm going to draw a dotted version of the cosine of this. Okay, so I want you to see how the cosine and the secant relate to each other graph-wise. If I were to draw the cosine on my diagram here, my bad art, it basically looks something like that, right? I guess I didn't draw it dotted, but okay. So there's your cosine, and I'm going to go ahead and continue it on over here. Okay, so essentially something like that, right? Okay, what the secant looks like, and again, if you plot enough points, you can see that this is a fact. I'm not going to take the time to plot 300 points here, but ultimately the secant does this. Okay, keep in mind that the cosine is positive in these two quadrants, the first and the fourth. Okay, these two represent first and fourth, between 0 and pi over 2 and 0 and negative pi over 2. Okay, so if the cosine is positive, then shouldn't the secant be positive also, since it's just the reciprocal? Okay, and what the secant looks like is this. And let me draw it a little better here. Okay, so the secant comes down to 1 from the left. Okay, and 1 is a minimum for it, and it goes back up. Okay, you might say it looks like a parabola, but it's actually kind of a little bit flatter at the bottom than a parabola if you plot enough points. Okay, And in this area, same thing, except for it goes up to negative 1. Whoops, negative 1 that is. Actually, I went down too far. Darn it. My art is not very good. So skip that right there. So we're going to actually go up to negative 1 and then back down towards the asymptote. Okay. So let me do that again over here in this area between the 0 and pi over 2. We're going to come down to 1. Okay. And we're going to go up the other asymptote. Same thing over here in this negative area. We're going to go up to negative 1, down the other asymptote. Okay. So when you get finished, you're going to have a bunch of what kind of look like parabolas. Okay. You're going to have one in the middle that's above the x-axis, one below, one above, one below, one above, so on. And in this case, I want to talk real quick about the period. How about the period here? Keep in mind that if I have a positive 1 and a negative 1, I go back to the positive 1 here, so the period is actually from negative pi over 2 to 3 pi over 2. So just like sine and cosine, the period here is 2 pi. Okay, we go 2 pi before we start over. So tangent and cotangent, both periods are pi. Sine, cosine, secant, cosecant, the periods are all 2 pi. Okay. Questions on that one? All right, let's take a look then at the final one, which is the cosecant graph, which is of course defined as the 1 over sine, which means that wherever sine is 0, we're going to have asymptotes. So we're going to have an asymptote at 0. We're going to have an asymptote at pi. We're going to have an asymptote at 2 pi. Negative pi. Negative 2 pi. Okay, and like I did with the sine function, I'm going to roughly draw the, or like I did with the cosine, I'm going to roughly draw the sine function in here to show how it relates to the sine function. Okay. So that's our sine function. We're going to put it on the same graph as the sine function. Okay, and that kind of dictates where the parabola shape is. Okay, in this case, it's got to be above because we're in the first and second quadrants. That's where the sine's positive. Third and fourth quadrants, sine is negative, so therefore we have the negative branch. Negative branch over here, third and fourth quadrants again. Positive branch here, first and second quadrants again. And so again, the general shape looks almost exactly the same. If you were to compare the two graphs that I just drew, okay, do they look much different? What's the difference then? The asymptotes are the difference. Okay, and where the function equals 1 and negative 1. Fair enough? Questions so far? Okay. The next part I want to look at here then is if we're going to take any of these general functions that we just outlined and graphed, okay, that if we were to make any transformations, okay, how might that look? So we're going to go ahead and take number 26 from your book. It's on page 402. And I'm going to illustrate the method here. And we can ultimately use this method with any of these 4 functions. So if this was tangent or cotangent or cosecant, we'd pretty much do the same thing. Okay? And in this case, we can see that we have a couple of issues here. We have a negative 2 out in front. We also have a half here. Okay? And so when I see that, what I'm going to do is I'm going to make my coordinate plane. Okay. I'm going to make 4 tick marks on either side. Okay. And then what I'm going to do is I'm going to establish what the asymptotes are. And that's probably 90% of the battle, is making sure you can find the asymptotes where they belong with any of these 4 functions. Okay. All right. Now, you can do first if you want to. We normally know the period is 2 pi, but just like for sine and cosine, the period is going to be 2 pi over b. So therefore, our period in this particular case, 2 pi over a half, is going to give us a period of 4 pi. Fair enough? All right. Now, you'll notice that I didn't put 4 pi right away like I do with sine. Normally I'd put 4 pi right there and I would start drawing my picture. Right? Okay, I don't want to do that quite yet. I want to figure out what the asymptotes are. Fair enough? So what I'm going to do is make a list of the asymptotes of the normal secant function, which the normal secant function, keep in mind that cosine's on the bottom. Okay. So cosine is equal to 0 at pi over 2, 3 pi over 2, negative pi over 2, and negative 3 pi over 2. Now, my advice to you is I would use those 4 every time to start with. Fair enough? So use those 4 to start with every time. Okay? So these are the original asymptotes. Okay, to get the new asymptotes, okay, what we're going to do is we're going to divide by b. Okay, I'm going to put the absolute value of b here too, because b theoretically could be negative. Most of the time it's not in our case, but so we're going to divide by b. Okay. Now keep in mind here that b is a half in this case. So when I divide each of these by a half, I'm really instead multiplying by 2. So that means that negative 3 pi, negative pi, pi, and negative 3 pi are going to be my new asymptotes. Fair enough? Okay. So I'm really going to do it just like I would do the period. If I can find the period by dividing by b, then I can find the new asymptotes by dividing by b. Okay, and what I want to do here then, okay, is I want to put those onto my coordinate plane. Okay. And I'm going to use my 4 tick marks as the guides for where I'm going to put those things. So I'm going to go ahead and put pi here, 3 pi here, negative pi here, 3 pi here. Now if you want to spread it out more, you can put those on the second and fourth one if you want to. That would make your picture a little more spread out. It's kind of up to you as long as you have it labeled okay. I don't really care which way you do it. Okay. So go ahead and put them on those 4, or like I said, you can put them on the second and fourth. It's up to you. Okay, so no matter what I get for this, okay, should what I do here change? Okay, and as soon as I plot those points, I'm going to make my asymptotes. Whoops, you know what? I lied. I need to skip a tick mark, sorry. I'm going to put them on the first and third. Sorry. So I'm going to put my asymptotes here, not on there, but keep in mind they need to be 2 pi apart, so it wouldn't make sense to put pi and 3 pi next to each other if I'm going to count those as 1 pi. Okay. All right, so there's my asymptotes at negative 3 pi, negative pi, pi and 3 pi. And then from there I can go ahead and plot the graph the same way as I normally would, except for one thing. Okay, we have this negative 2 here to deal with. Okay, so that negative 2, okay, keep in mind that between the middle 2 asymptotes, I would have just made a point at 1, and I would have made that parabola shape. Okay, but the problem is we have a negative 2 here, so think about what would that do to our normal parabola shape. The negative is going to make it go where? It's going to make it go down here now. Okay, and the 2 part, remember, keep in mind 2 would make the sine or cosine get higher. Okay, and if the cosine gets higher, then what's the secant going to do? It's also going to go up as well. So what we're going to do is we're going to plot that point at, instead of 1, it's going to be plotted at negative 2 then, isn't it? Okay, and then general shape-wise, okay, it's going to be pretty much the same general shape. And I'm not going to be too picky on the general shape here, because if it does have a bigger number up here, the shape actually gets kind of skinnier, but kind of hard to tell. Remember we talked about having a vertical shrink. It's kind of hard to tell if it actually vertically shrunk or horizontally stretched or whatever. Okay, in this case it's a vertical stretch, if you will. I think I said that backwards, but if it's a vertical stretch, it's going to be a little thinner. Okay, but I'm not going to be real picky on how thin it is. I'm more concerned about the asymptotes and actually where your curved parts are. Okay. Now in the second one, it should have come up to negative 2 here normally, but instead it's going to come down to 2 because of the negative. Okay, so there's one cycle, and of course we could draw another cycle over here. And we could keep drawing cycles left and right, however many we needed to, and we'd be good to go. Okay, questions about that process? Alright, so what I'm going to have you do right now is take a look at one last problem that I want to consider. We are going to have some problems in our homework that ask us to solve an equation involving some of these functions. Okay. Most of the problems are going to be solve it graphically, because there's really not a good algebra way to solve that particular equation. So with your calculator, if you graph x squared and you graph 1 over sine x, because you don't have a cosecant button, you should get the following picture. A lot of times your calculator will draw the asymptotes. Make sure you recognize that that's what they are, and they're not part of the function, they're just asymptotes. Okay? And the question says smallest possible number x such that these are equal. Ultimately here you see two intersection points. Okay? So they're after this one right here, smallest positive one. Okay? So of course, just like any other intersection problem, you can just use your intersection command and find the answer without too much trouble, without doing any algebra whatsoever. Okay? Alright, so the other thing I'm going to mention too as you're doing your homework today, okay, make sure that you send me ones that you're having trouble with, especially if you get some like these that have transformations involved, okay, because we'll do a couple more of these together tomorrow when we do our homework together. Okay. Other than that, you can go ahead and start working on your section 4 or 5 homework problems, and that's it.